So as I was saying, it's possible to use RNNs for other language tasks like speech tagging, for example. So for part2 speech tagger, the output will be softmax distribution over the possible POS tag. So training an RNN to do classification like this, to determine the part of speech, is going to be done the same way. The only difference is that the training data will require labels. So in that case, part of speech tags. So that will make it harder to collect data than in the case of developing a language model, just because for the language model, all we had to do was just shift the words by one time step. So notice that in a language model, we're always interested in predicting the word at time step t+1, given all the words up to time t. But for classification, why would we limit ourselves to only the previous words? We could maybe use words that also occurred after the current word to help us identify the part of speech, right? So we would need some kind of look-ahead architecture that feeds into the current hidden layer both information from the previous words and future words. Okay, so looking ahead in that case can be very helpful. So that gives a possibility to what we call a bidirectional recurrent neural network, which concatenates a separate right-to-left model on top of a left-to-right model. So it will go both ways. Okay, so this is sample architecture. You can see that it has one model going from left to right and one model going from right to left, and they both feed into the current hidden layer to make the probability distribution over the different part of speech. So in the case of a multi-layer RNN, ZT will be the hidden vector of the last layer, but for a bidirectional RNN, ZT is usually taken to be the concatenation of vectors from left to right. Okay, so in the previous structure we looked at, if we're interested in ZT, then it's typically the last layer up to that time t, but in bidirectional, of course, it's not. Now, RNNs can also be used for sentence level or document level classification task, in which a single output comes at the end. Okay, maybe I'm not interested in intermediate outputs, y1, y2, y3, and so on, and I only need one output after the entire text is processed. For example, in the case of sentiment analysis, maybe I just want to read the entire review that was given, and then at the end, after I read the entire text, just decide is that positive or negative. Okay, so in that case, I'm only interested in one output, which is y at the end of the sentence. So using RNNs for this type of task is a little bit more complicated, since we need to essentially aggregate the whole sentence representation y from the per word output yt of the RNN. So the simplest way to do this is to use the RNN hidden state corresponding to the last word of the input, since the RNN will have read the entire sentence at the time step. So essentially what we do here is the only thing we care about is to calculate the loss using y3. okay, which is the final output. So say y3, we pass it by a sigmoid function and get a probability, for example, over negative or positive, just two labels, and then compare that to the true label that we needed to predict. So the problem with that is our entire decision is only based on the final hidden layer, which is Z3 in that case. Okay, so this can implicitly bias the model to pay more attention towards the end of the sentence and forget what was said earlier in the sentence. So another approach is to pool together or take the average of all the hidden layers and then feed that into the sigmoid layer to get finally a classification between good and bad. So in that case, we are forcing the network to pay attention not just to the last hidden layer Z3, but also to what was said before we reach Z3. Okay, so this is how we can use that same structure for sentiment analysis or single item classification. Now, as we saw, it's possible that as the network gets longer, that it forgets about what was said earlier in the sentence. So RNNs mostly will solve the limited context problem because in theory any information could be passed from one hidden layer to the next for any number of time steps. But in practice, the information can get lost or distorted. Okay, so by the time a word that was said way earlier in the sentence reaches the final layer, it's probably not very accurate. So this problem for INNs is similar to the vanishing gradient problem that was discussed in feed-forward network. If you use a network structure that's very deep, by the time the gradient, you calculate the gradient with respect to, in doing backpropagation with respect to the last layers, you will almost have zero gradient. So your network will have a very hard time converging in that case. So this is very similar to what we have here, except here we're not losing the gradient, we're losing the meaning from the very first words in the sentence. So one approach to resolve this problem is to use long short-term memory, which is a variation of RNNs that uses what's called gating units. So these LSTMs don't suffer from the problem of imperfectly reproducing a message from one time step to the next, because gates help us choose to remember some parts of the input, copying it over to the next time step and forget other parts. So we're not gonna just incorporate the input into the hidden steps. Now we will copy input parts as they are to a further step without modifying them. So by copying feature forward without any alteration or any change until it is needed to make a choice, this way we can reduce the problem of this vanishing gradient or forgetness for RNNs. So for example, there's a nice example in the book. Consider, for example, a sentence like the athletes who all won their local qualifiers and advanced to the finals in Tokyo now, and at this point we're trying to predict what comes after now. So is it compete because we're referring to the entire athletes, or competes? Okay. Now in this case we know the subject are all the athletes, so it should be compete. So if we train an LSTM on this sentence, it will learn to create a feature for the subject person, a number, and copy that feature forward without any change until it's needed to make a choice like this. On the other hand, the regular RNN will get confused in sentences like this one, okay, because it will forget who's doing the action, who's the subject here. Now, another applications of RNN is machine translation. So in this case, we have what we call a sequence-to-sequence mode. Okay, so the goal here is to translate a sentence from one source language to a target language. Now, obviously, as you can imagine, we can't just translate word by word, right? Because we have to observe the grammatical differences between one language and another language. Okay, so in many languages, for example, the adjective comes after the noun, other comes before the noun, and so many other grammatical variations that we can just translate word by word and say this word corresponds to that, this word corresponds to this, and so on. So we have to consider the context in each of the languages. So one of the most this is one of the most widely application of recurrent neural network. So in that case, we have to train this machine translation network with a large corpus of source and target sentence pairs. The goal is then to accurately translate new sentences that are not in the training data. So how can we use an RNN to create a machine translation system like this? Now, we learned already how to encode an entire sentence when we did sentiment analysis. So we pass word by word, and at the end of the day, we just make a decision based on the sentiment, based on that last hidden layer, on the output from the last hidden layer. So, of course, if the task was as simple as to do one-to-one correspondence translation, word by word, that would be easy. That would be similar to the part of speech tagging. So you would take a sentence in English and then just tag each word with the corresponding sentence in Spanish, for example, and train a classifier on that. Okay, but as we said, that's not going to work in translation. The book, for example, mentions some examples like, for example, the word seahorse in English, which is one word, actually translates to 3 words in Spanish. And word reordering can be even more extreme. Okay, like I said, so in English, the subject is usually at the start of the sentence, but in Fijian, the subject is at the end of the sentence. So how do we use the RNN then if we can just tag each word like part of speech tagging? So then what we need to do really is to generate the target sentence one word at a time, but to keep track of the context so that we can remember parts of the source that haven't been translated yet, and keep track of what has been translated so that we don't repeat ourselves. It also seems that for some sentences, we have to process the entire source sentence before starting to generate the target. That would make sense. So we read the entire source sentence, and then, based on the output from that last hidden layer, we can feed that into a new RNN whose job will then be to generate a sequence of words in the new language, which is the target sentence.